Okay, so hello everyone. So we're going to move into the second section of your unit 3. Under this section, basically what we are planning is continue of your earlier section. That means chapter 22. This will be second part of that. Right. So now we need to understand these two things separately. So first thing in chapter 22, that means your earlier section, we start the magnetism. We discuss about magnetic force when there is a charge particle moving inside the magnetic field. That is one concept. And the next one is if there is a current carrying wire inside the magnetic field, there is a magnetic force. Basically, what we did is we discussed about how to define magnetic force and also magnetic field. But in this part, our plan is to basically discuss about magnetic sources. What that means is, how do we create magnetic field? First thing is by using the magnets, as we discussed. If I have two magnets, definitely I can create the magnetic field in between those, right? But in addition to that, is there are any other methods that we can create magnetic field? That will be the magnetic sources. Then we're going to talk it in this section. Okay, so now according to your chapter, your section will be definitely second section in unit 3, but under chapter 2 yet. So now within this chapter, we're going to talk a little bit about Biot-Savart law and Ampere's law. These two laws, basically Biot-Savart, we are not going to discuss in detail. That will be for advanced level physics classes or Cal-based physics classes. But here, what I'm planning to do is basically give you some idea about what is the Biot-Savart law and what is the Ampere's law and why we use Ampere's law for your simple calculations. And then we're going to move into the force between two parallel wires. If there is two parallel wires, they can have the attraction and repulsion according to the magnetic force that we discussed in earlier section. We're going to combine that into the magnetic field that we create by using one wire on the other wire. And then we're going to move into the solenoid, spiral shape wire, and then toroid, circular shape kind of wire that we have the spiral that bend into the toroid shape. Then how this shape of the object will create a magnetic field, and where that magnetic field will create it stronger with respect to inside or outside. Okay, so those are the things that we're going to discuss in this chapter. So now, first thing, I'm going to move into the magnetic field due to current carrying wire. So now, everybody know that if I have a magnet, definitely that will create the magnetic field, right? So, but in addition to that, if you have current carrying wire, which will bring a current, we'll say there is a current on this wire going upward direction, and then this wire actually create the magnetic field depend on the strength of this wire and also distance to that wire, but it will create a magnetic field everywhere around this wire. But how it will create? It will create in very specific way, because magnetic field lines should be a circular path. That means magnetic field lines will create around this wire. Everywhere on this wire, around the wire will create the magnetic fields. But to calculate this magnetic field strength, Biot-Savart is the scientist that actually discussed how to calculate the magnetic field for not only for this kind of wire, but also for any kind of shape of the wires that we have. Anything that you have current carrying object or wire, that will create a magnetic field. That magnetic field will be able to calculate by using Biot-Savart law. So Biot-Savart law basically explaining that you need to calculate by taking small pieces, you need to do the integral and do the calculation by choosing the point of your object and by adding each terms into that. But Biot-Savart is explaining how to calculate it, and also it will explain the direction of the this magnetic field, right? So now it seems little complex to use it because we need integration in here. Because of that, we are not going to actually use it. But Biot-Savart law is the best law that we can calculate the magnetic field by using any kind of any shape of, without thinking about the symmetry. You can use the Biot-Savart law, right? Any object, it will work. Now, to understand, there is a very important parameter in here, because you remember that in electricity part, we use the epsilon naught. So that is the permittivity of the air or the environment. But here is the mu naught. Mu naught, we call it as permeability, is a constant. And again, you have the value in this way. So usually we use this value because it is easy to use it, but it is up to you. Both are the same. Okay, so now there is a Biot-Savart law. You can apply this rule to current carrying wire. If you have current carrying wire, if your pointed interest is here, distance from wire to there is R, then you can calculate the magnetic field at this point because of current on this wire. That's the equation that we can get from Biot-Savart law, right? So now it will explain the strength of the magnetic field by using I. If I is greater, B will be greater. But if R is greater, that means you are going further away from the wire, then your strength is keep decreasing. Strength will be stronger closer to the wire, then keep decreasing 1 over R ratio to when you go away from the R. Okay, 1 over R shape graph. Okay, so now, since we discussed the magnetic field earlier, it has the direction. Now, direction is explained by using Biot-Savart law, but to get that direction easily for our case, we can use again the right hand, but this is a different rule from the earlier right hand rule you discussed. Earlier right hand rule, I had 3 directions that we discussed. In this case, I just have 2 directions. Basically, I have current and the magnetic field, only 2 vectors, right? So current, what you need to do, take right hand. Again, you see the mirror image. This is my right hand, not left hand. Okay, so you take right hand, your thumb is going to point into the current direction, and then you're going to grab the wire. When you grab the wire, if current going up, my thumb is pointing up direction, then you grab it. When you grab it, you basically moving this way your magnetic field. That means in here it is inward, going to the left, outward, going to the right. That will make a circular around the wire, right? That will be the direction of the B. Okay, so now next one is actually Ampere's law. So Ampere's law, I can say it is a narrower region that you can use. The Biot-Savart law is a spread version, that it is a detailed version that you can use for the wide range. But Ampere's law, you can use Ampere law, you can use for the narrower region. That means we're going to focus into only symmetrical object that where Ampere's law can be used, right? That's the simple version of the Biot-Savart law. So now what the Ampere's law say in that, you can calculate the magnetic field by getting the total current and by choosing your closed loop. As an example, if I have a current wires, you know that this is going inside current, this is outside current, this is outside direction. But if I choose my Ampere loop, this is called it as Ampere loop. If I choose my Ampere loop, if I know total current inside, that is called it as I enclosed. In this case, it is actually I1 minus I2, because I1 going outward, I2 going inward. Then you have basically difference between these two. I enclosed. you need to think about what is inside current is, that is what I enclose means. And then you going to take the circumference of your Ampere loop, that should be a closed loop, and then you're going to divide that by circumference of that loop and times the mu naught value. This will give you the B value, right? So now, simple example, if I have a current and if I choose my point of interest here, I make the Ampere loop exactly a circle that will go through the, outside of this wire. That means I can calculate the magnetic field exactly same distance in different places, right? Simple example, if I have current carrying wire I, if your point of interest here, then you're going to calculate the magnetic field going inward, outward, but distance R, then this B will be equal to, your loop is this one, this is the closed loop you're going to select. Then you have mu naught times current inside is I, as I have, and you're going to divide by circumference of that 2 pi R. So this is what the magnetic field for current carrying wire. It is exactly same as this equation from Biot-Savart. So by doing longer calculation, you can get into that. But by thinking the simple way is the Ampere law, you can easily calculate the B. Okay, that is the Ampere's law. So now definitely if I have a current, this is outside current, right? Then your magnetic field, you have a current this way into point my direction, you're going to grab the wire by pointing your thumb towards the tip of the your current, and then your direction of the magnetic field will be this way. Now inside this loop, anywhere in this circumference, you should have the same magnetic field, but direction is changing according to this, it is counterclockwise direction, right? So that's why I have B is proportional to R if it is greater than the radius. But if you have a very big wire that you need to get the magnetic field outside, we know how to calculate it, but inside there is an inside magnetic field also, theoretically there should be, that will be able to again calculate by using the current density that we discuss in your electricity part, because current density is basically current over cross-sectional area of the your cylinder, right? So now by thinking about that, how much current inside that small piece that you're going to select, as example, if your wire cross-section is this one, if you select this area, your current is basically distribute to whole this blue surface, but you are only interested with the this red area, then you need to take the what is the current inside that will give to your solution that you need to use the Ampere law, right? So that means enclosed current will be this red area current, not everything. So because of that, your B will be finally proportional into R. So that is what happened if you do that calculations, that we are not going to do it here. We are just discussing how these formulas will work, right? Then your formula will be turned into actually this one. But why we need inside current? Basically, we are interested on outside of the wire. Most of the real life applications, we are not much interested on the inside the wire. So we will going to focus into the outside magnetic field. That will be this one that we can calculate by using total current of the wire. Okay, so now we discuss two things. One is how do you calculate magnetic field if there is current carrying wire, that magnetic field will be going around the wire. So one thing is calculating magnetic field by using this formula. Other thing is taking the direction by using your right hand. So these are the two things we discuss. Okay. Okay, so again, here it will explain, apply your right hand rule and to different places, right? So as example, if you have a current going downward, you use your thumb to the direction of the current, that will be this way. And then you're going to grab the wire, then you have this direction of the magnetic field. And then magnetic field is stronger in here weaker and getting weaker when you go away from the radius. Okay, so now this is another view of the same thing. You have current outside of the board, then you point your thumb to the direction of that, then you have this direction that is basically counterclockwise direction. And if you have invert, that will be basically clockwise direction, right? So different view of your current carrying wire. Okay, so now I have this example, which figure represent the B field generated by the current. So now check the first one. You have thumb outward direction, grab your blue wire piece, and when you grab it, you have magnetic field this way and magnetic field outward. That means this is incorrect. Correct one will be this one. Okay, none of the others are correct. And the same question again, you have current outward direction and you're going to grab the wire, then your direction of the magnetic field will be basically counterclockwise direction. That means again, this one is the correct one. Okay, so now magnetic field, we discuss about lone wire which carry the current. It is actually some assumption. If you have a small wire, that we cannot use that formula directly. Okay, so we are doing the calculation by using some kind of assumption. We have lone straight wire, then we can calculate the magnetic field by using that formula. So now I don't have the lone wire. What I have is a circular shaped wire. If I take the circular shape wire, we'll say I have a piece of the wire that has a kind of bend, like make an arc shape, right? So now I have a current going upward direction. Is still your right hand going to work, right? So you have a piece of wire. You're going to see that your current is going this direction, and then you're going to point your thumb and grab the wire. So when you grab the wire, your magnetic field will be in this place. Your point of interest is center. That will be outward, but this side, it will be inward. But I am interested calculating magnetic field at the center of the piece of wire. Okay, that's what we are interested in here. So now center magnetic field due to arc-shaped wire will be able to calculate by using this formula where this is came from. This is actually Biot-Savart law. You cannot use Ampere law to calculate this. And you need to use the Biot-Savart law to calculate that. It's long calculation, but this is the formula for that, right? So now mu naught I 4 phi r, we know what it is. R is a constant in this time, right? So now phi is the angle that you make the arc shape. It is very important in here. This phi that I have it in here should be in radians, not in degrees, radians. Okay. So now what that means is, after I know how to use this equation for the arc shape, if I have a half a circle, I know how to use it. If I have a full circle, I know how to use it. What will change? Only change in variable in here is the radian angle. Other than that, everything will be the same, right? So now if I have a full wire, you see that the magnetic field lines, this blue, the green color lines are the magnetic field lines. You think that your thumb is pointing this way, grab the wire, then that's why I have the magnetic field lines going inward in this side and outward in this side. In the wire piece, if I have this kind of wire, basically, not have a wire piece, but I'm going to take this one. I have this kind of wire, right? Then you have the current going in this direction, this way, all together. I have a wire that carried current this direction, right? So now I need to, in this way, this case in opposite direction, this direction current carry, then you're going to grab the wire. When you grab it, your fingers go inside, out, coming in this direction, right? So that will be the magnetic field direction. That's why you have those are outward and bottom it is inward, right? So now if it is a full circle, what will happen to this equation? Then your phi will be changing into 2 phi, right? Then your B will be derived. Then B can be derived mu naught I 2 phi divided by 4 phi and R. So then 2 pi and this cancel out. 2 will be left. That means for full circle, we have B equal mu naught I over 2 and R. Okay, that will be for the full circle. If it is a half circle, then your pi will be just pi radians. So then you need to accommodate according to that, right? A good example that we can see it on the laboratory is Helmholtz coil. Helmholtz coil, actually, we do not do that for your class in the laboratory because it's a big setup that we need more coils and they are expensive and not able to use it. But actually, this is the application of this magnetic field phenomena that we are learning. So if I have, there are like 100 turns in this one coil, 100, 200 turns, or some of them 500 turns, then coil radius is different, right? Then they will create the magnetic field as we discuss in here. So now if you combine two coils, we call it as a Helmholtz coil system, then your magnetic field lines will be that kind of thing. So you will be able to actually observe magnetic field on your x-axis by traveling, by keeping magnetic sensor, you will be able to observe the magnetic field. As you can see it in here, single coil will create this one, double coil will create this one, and overlaps of both coil will be together, will create the magnetic field at the center is stronger, right here. So a stronger magnetic field will be created. So now, this is the application that we can see. We are using this in many places, but this is the real life application that we can see it. So now next part is actually discussing about current. So current carrying wires, that I have many wires, right? If I have two wires that will carry the current, they can carry the current in same direction or they can carry the current in opposite direction. So when they carry the current in the same direction, actually these two wires going to attract each other. If it is a wire, this is a plastic, that's why it's not going to bend, but if it is a wires, they're going to attract each other. If they go in opposite direction, they're going to repel each other. Now we're going to understand why this is happening, right? So why it is happening? So we'll say I have a piece of wire. And this is similar to that, the magnetic, the electric field created by different charges in different places, similar to that, right? If I have one wire, we'll say I have one wire in here that will carry the current I. So now, if this is my point of interest, we already know there is a magnetic field at this point. We know how to calculate it. Mu naught I divided by 2 pi r. We already know that. But if somebody try to bring a wire, another wire in here, okay, so bring another wire that will carry the current. We'll say again I, we'll say IA and IB, current IB, right? So now what happened? So now I have a current carrying wire inside the magnetic field. That means you need to go to your earlier section and think about what is the force for that wire is, right? So this B, red B, created by red wire on blue wire. Now blue wire is in magnetic field. Because of that, there is a magnetic force. What is the rule? You're going to use your right hand rule. Your I will be thumb and this will be your magnetic field, then thumb will be open to the force. Now if I use it, what will happen? So magnetic field, I did not label the direction. You know that the direction of magnetic field on this wire due to the red wire will be inward in this place, inward, right? So now you have the thumb upward and magnetic field inward, right? So that means my thumb going to be open to my left side. Okay, so when I open it to the left side, direction of force on this wire will be actually this way. Force direction of wire B due to actually current of wire IA, right? So now you think exactly same thing again. You keep the blue wire, then you find your point of interest somewhere here. Because of the blue wire, it will create the magnetic field on here. that will be actually outward direction. This is B. I'm going to say this is created by A, this is created by BB. Okay, so now because of that magnetic field, you have current upward, magnetic field outward. Now use your rule. So then your magnetic force will be to the left. So now this will create a magnetic force to the left. I'm going to draw it somewhere here, magnetic force to the left. So now because of these two forces, these two wires going to attract each other. It is the two concepts that you learn in earlier section 1 and section 2 together will make this connection, that they will going to attract each other, right? And they will repel each other if they have opposite current. Same principle you can use yourself to practice it. They're going to repel each other, right? So now, how do we calculate this force? We definitely know how to calculate the force, because FB that I labeled in here calculated by using, FB is calculated by using current of that wire, that is IB, and length of the wire, I'm going to take the length L, right? And then magnetic field on that wire due to the other one. So that will be B times A. And angle between these two, definitely sine of 90 is 1, right? Sine of 90. Okay. So that will be the magnetic force that create on the other one. So you do exactly same thing for the FA. FA will be IA times L times B, BB, right? So now these two are equal and opposite always, because they have a connection. These two are equal and opposite always. If you calculate and check if they have the same length, then they will be equal to each other. Okay, so so that's how this will attract and repel. So now moving to our last part, solenoid and toroid. So solenoid is the coil of the spiral shape loops of the current carrying wire, similar to this one, right? So when there is a current, you see that it is going inward, it is coming outward. Then again, you're going to use your right hand rule, point your thumb to the direction of the current, and then you're going to see your magnetic field will be pointing in this direction, right? So it is in solenoid. We can actually do the calculation by using Ampere's law, but we are not going to do it. We're just going to use the equation. What is happening is, inside your solenoid, there is a strong magnetic field, but outside there is magnetic field that we can actually ignore those things, right? We are interested inside the coil. Inside the coil magnetic field, by using Ampere's law, we will be able to calculate by using this equation. So mu naught permeability, I is the current that passed through the solenoid, and N is called it as number of turns per unit length. Okay, number of turns per unit length. If you have N number of turns, divide by how much it distributed, the length of the solenoid, and then you're going to calculate the N. Okay, N is the number of turns per unit length. Okay, units is turns per meter. Okay, so usually the solenoid will work as the magnet, north and south magnet. If you have a current in going this direction in this each coil, if this is the current direction, you're going to use your thumb and then you point your, grab the wire, then you see that your magnetic field is pointing in this direction. That is actually the north. Okay, similar to your north and south poles. Okay, so next one is toroid. Toroid is basically a circular shape that you make the two end of the solenoid and make the connection to make a solenoid, right? So this kind of shape. And so to make a toroid. So now what is the difference between solenoid and toroid is, so your current, if you watch the top view of the the top view of the toroid, you will see that your currents is going, see that current is outward here and inward here, because your loop is going like this, right? When it go inward, outward, inward, outward. So each portion of each turn of the wire have the same features. So now in toroid, you can again use the Ampere's law to calculate it. But if you calculate the magnetic field on the toroid, your equation will be this one by using Ampere's law. Okay, so now why it is different than the solenoid? Because you see that in the solenoid, you have the magnetic field constant inside the solenoid, right? But toroid, you see that your magnetic field in here is different from here to there and here to there. Because why? Because your radius is different for this each point. Different radius. Because of that, they have different magnetic field. So now my formula will be equal to mu naught I n over 2 pi r. This n is actually not turns per unit length. This is number of turns. Okay. So now toroid, inside the toroid, you can have different magnetic field. You cannot say it is a constant like solenoid. Okay. Okay, so to get a little bit understanding about magnetic flux, since we discussed about electric flux earlier, electric flux is basically saying that how many electric field line that cross through the surface, we call it as the electric flux. We calculate it by using E times A times cosine of theta, right? Similar to that, magnetic flux also there. Magnetic flux is saying that how many magnetic field lines can cross through the surface that you are looking for. Then that we call it as magnetic flux. We will be able to calculate by using same formula, but B times A times cosine of theta, right? What that means is when you have the plate that you are working right like this, if the magnetic field is going this way, that means you see that my magnetic field is parallel to the cross-sectional area. In that case, I have strong magnetic flux, right? But if I have magnetic field going in this way, that means my cross-sectional area and the magnetic field are 90 degrees. Because of that, cosine of 90 will give you 0. That means there is no magnetic flux when they are staying like this. So that's the idea, okay? So units, Tesla meter squared, you see that it is measured from Tesla and meter squared in here, right? So that we call it as Weber. Okay. Okay, so now again, we are not going to discuss those things in mathematically by using detail-wise calculations. We are just try to understand the little bit background about this magnetism. So now there is a Gauss law in magnetism. Gauss law in electricity also there. Remember that we discussed that part. And similar to that, there is a Gauss law in magnetism. So Gauss law in magnetism is saying that actually no monopoles. We already know that magnetic monopoles do not exist. Right? So that is the Gauss law of magnetism. There is no magnetic monopoles. That's what it is. Okay, Gauss law of magnetism. And last part of this section, I'm going to talk about where this magnetism coming from. So we talk about the magnetism. We are seeing different magnets. We see the ferromagnet, paramagnet, diamagnet, different magnetic materials, right? All the materials we have different kind of behavior of the magnetic moments. So now magnetic moments, you know that you always staying with north and south poles. That means there is a moment that is called it as magnetic dipole moment, right? So now simple example is if there is an electron, we know that electron is traveling around the nucleus. This is nucleus. Electron is going around the nucleus. When electron travel, that is basically actually a current going opposite direction. That's what the electron means. The things that we discuss in electricity part. So now when this electron going around the nucleus, so that electron, basically the system will create a angular momentum. We come to your physics 1 class. The angular momentum is pointing, if there is velocity of the object pointing this way, we know how to find the angular momentum direction. That will be the direction of this one. Okay, so now similar to your current rule, you point your thumb to the direction of the angular momentum, then you have direction, velocity in this direction, then we will get the magnetic, angular momentum direction, right? So now angular momentum direction is not actually moment direction. Moment direction is actually magnetic field direction. B and moment direction will be the same. But that means is you need to think about your current direction. You're going to use your right hand rule you learn and point your thumb to the direction of the current, not to the electron direction. Current is opposite direction. And then you're going to grab the wire. When you grab the wire, your magnetic field point in this direction for all of them. So that will be the direction of the magnetic moment that I label it as mu later in here, magnetic moment. Okay, so magnetic moment of the take the eraser. Okay, so I'm going to take the eraser, but it did everything. So now this is the magnetic moment is. Okay, that's the direction of magnetic field. So now how to calculate this? I'm not going to do detailed calculation. So it is a combination of classical atomic system and also quantum physics that will combine later on to discuss about those angular moments and things. But classical picture of that is actually we can calculate the magnetic moment by using charge of the electron and mass of the electron and the angular moment. That's the way that we can calculate the magnetic moment. Okay, due to electron traveling on a circular path by keeping nucleus at the center, right? But in addition to that, as you guys know, electron will spin itself. Electron rotate itself and then go around the nucleus, rotate and going. That's what happening usually, right? So now because of this electron spinning, there is a spin magnetic moment. There is a spin magnetic moment and there is a spin angular momentum. So now spin angular momentum will be pointing this way, similar way that you use your right hand and the key fingers where the velocity direction is, then thumb will give you the direction of angular momentum. But mu will be always opposite to that one because we are not working with the electron. Mu is defined for the proton, right? Or the positive charge, or the other side of other direction of the electron, opposite direction of the electron. So now magnetic spin moment will be able to calculate by using this formula. So now H cross, we call it as a Planck constant. That is a constant that we can get it easily, and then you can calculate this. But important thing is Bohr magneton that probably you have discussed in your chemistry class or somewhere. Bohr magneton is the basically magnetic moment of the electron in any atomic system. That is called it as a Bohr magneton. That will be basically calculating of this value that will be closer to the answer that I have it in here. That is called it as Bohr magneton. Okay, now somebody can think why we are only talking about electron, why we are not talking about electron, the protons and the neutrons. So protons and neutrons are sitting on the nucleus, right? So protons actually can have the moment, but it will be very, very smaller than the electron because electrons are the particles that move around, right? Because of that, we can neglect those moments. Okay, so now since we know a little bit about what the magnetic moment is, this part will describe the different magnetic materials. The first one, we're going to discuss the ferromagnetism or ferromagnetic materials. So ferromagnetic materials basically have magnetic effect that we can have it in iron, cobalt, nickel, those kind of materials, right? So the permanent, this basically contain the permanent kind of magnetic moment that will keep keep inside the magnetic field and also outside the magnet. That's what you have it in your refrigerator. Those are ferromagnet, that we can have the magnetism although it is outside of magnetic field. Those are, we call it as ferromagnetic material. They may have some domains that we have opposite direction of the magnetic fields and those things, but basically it has the magnetism that created because of the magnetic field. But although you take that material outside from magnetic field, that is still going to stay the magnetic moment. Because of that, those are magnets that we call it as ferromagnets. Okay, so the magnetism of any material can be destroyed, right, by probably by using impulse, that you can drop the magnet. So very high kind of impact will basically destroy the magnetism. In addition to that, if you increase the temperature, but if you burn it up, the material, that will destroy the magnetism. We call it as demagnetization. That's where that Curie temperature discussed in when we talk that in your history of the magnetism in the last section. Okay, so those are, we call it as ferromagnet. Basically, when you have the magnet inside magnetic field, all the magnetic moments going to align into the magnetic field. If you take out from the magnetic field, still this will have the magnetic field, that is called it as ferromagnet. Okay, so in addition to that, there can be a paramagnet, there can be a diamagnet, right? Paramagnet is called it as, there is a still permanent magnet, but when you take it out from magnetic field, as example, if you have magnetic field lines create similar to the magnetic field direction, but when I keep out from magnetic field, this will not stay in same magnetic moment. They will realign and make it to non-magnet again. So those we call it as paramagnet. And diamagnet will be exactly same. If you have this magnet, this material inside the magnetic field, then magnetic moment will be aligned opposite direction than the magnetic field. If this is the direction of the magnetic field, moment will create in opposite direction. Then after you take out from the magnetic field, it is still going to destroy the magnetism. Those we call it as diamagnet, right? Different magnetism. And in addition to that, superconductors, basically we call it as perfect diamagnetism we can have in the superconductors, because superconductors will create a kind of Meissner effect that will have the magnetic fields. And then when you bring the permanent magnet closer to that, then these two objects going to repel each other. That's why we call it as levitation. Actually, it is repulsion in between Meissner effect created by superconductor and the permanent magnet. Okay. Okay, so that's the end of the sections.